Okay, great. So then we could continue with the topic of debugging. This is slightly a switch gear. So the example I used here is also not a Risk-Wagner, but you could easily translate this knowledge, transfer this knowledge about debugging to the example of the Risk-Wagner model. So before we talk about debugging, so debugging is the process. So in programming, so when you program something in the first place, most of the time it's not going to work perfectly, right? If you code something and then you try to run it and you receive some error. And debugging is the process to find out where your error is and then to fix it based on the feedback you receive, the error message. So reinforcement learning in a way. You do something and then you receive error, the feedback, and you find out where it goes wrong, you change it, and then you see now it works. So reinforcement learn, good. But before we go into the topic in detail about how to fix your errors, we can talk about what the best practice are. Because when we have the best practice, it is actually good to avoid making some errors, right? So here are some style tips regarding using STEM, but actually you can generalize that with any other programming. You program in R, in Python, in whichever programming language. So all these tips, they apply to all of the languages. The first one is to make it reproducible. So you do not want to be in the case that you program something and then nobody can use it. And even yourself, you cannot use it later on. This is not great because we are trying to make reproducible research. And I guess you're aware of something called replication crisis in psychology and social science, meaning that some of the high-profile research published in the past cannot be reproduced or replicated. And then this really caused crisis to our field. And back then, people don't really share their analysis scripts. They don't really share their data. They write the procedure regarding how to do it in their paper, but when the other people, they read it, they try to reproduce it, they can't replicate. And this is problematic. So a better way is to share it as open as possible. At the same time, make it reproducible. Say, if you share something that is not reproducible and there's meaningless to share it, right? You write something and nobody can understand it, and then how come they could reproduce it? So pay attention to that. Make it reproducible. And remember that the scripts, they are always good documentations. So when you write a script, you also write the comments. If you write something that you think you will definitely forget after 3 days, then that's the place you could insert a comment to remind yourself, your future self, to say, why am I doing this? Why this is interesting? And a quite helpful practice that I found is pretty interesting and also valuable is that if you are making a mistake in the first place and then you solve it by Googling it, then it's actually a good suggestion to give the link into your script. So you can write a hashtag, right? And then after that, you give the link so that you might encounter the same problem again, but you know where to look for the solutions by clicking the link. This is really a good exercise and practice. And here, another one is to save your seed. So this argument is dealing with the fact that we are using probabilistic programming languages with a lot of randomness. So every time there is so to record the MCMC robot, we want the MCMC robot to start from random locations in the beginning and then try to find the posterior. This is preferred that the MCMC robot, they start from random locations. But perhaps it's not a so good idea that every time they start sampling, they start from different locations, because this means each time they will start from a little bit random location, right? We just maybe want to be in the situation that every time we want to sample something, they start from the same location, and then we will always get the same results. Okay, good. So here, this is like, there are two sides of the same coin. So on the one hand, we want to have exactly the same results every time we run it. So then we have to fix the starting point, even though they are randomly selected, but each time we run it, they are the same, they are identical. This is on the one hand of the story. But then there is another hand of the story. You also might want to have a stable estimation of your parameter. That means no matter where it gets started, maybe here, maybe there, maybe somewhere else, they always can find the same posterior distribution. And this is another story. Okay, you have to make the balance. So where to go with it. So you can just basically ask me, okay, so how can I decide? How can I make the balance? I can tell you what I do. So what I do is that I have some data, right? I have some experiment, have some data, and then I code up some model and then run it, and some debugging process that you will see during this lecture. Some debugging process. And I run it, maybe the first run is not good, and then I change it, and it's also not good. And then it's quite likely that after a few iterations, one version of the model and one version of the run is stable, and you will just like it. The result is reliable, and you can use it, you can analyze it afterwards. And then this is the version where you can save the seed. So that basically means after running, you can retrieve what was the seed that was used, and then this seed can be saved so that after rerunning, at some point, if you want to rerun your analysis, you can use the same seed so that you will always get the same result. Okay, good. And then there is a note. This is quite important to be aware of. So if I have a seed is to generate random numbers, right? If you don't know what that means. If you use a seed on your local computer or server, wherever that is, if the seed is used on the same machine, then it's guaranteed that you will always get the same result, good. But if the same seed is used at another machine, on another machine, you might get a different results. So this is because the seed that is used by STEM, so here it depends on the hardware. So hardware means how your motherboard looks like, your CPU, your RAM, your memory. The seed of the STEM language is a bit tricky, so it depends on the platform. As long as you are within one platform, you get always the same results. But across platform, this doesn't really work so well. Okay, just be aware of that. This is not the same in R. So if in R, we say the seed equals 1, 2, 3, 4, at different platforms, wherever you are running the code, you always get the same results. But instead, this doesn't work here. Just be aware of that. There is no solution. I don't know. So if you want to get exactly the same results between two computers, two machines, I don't know, no solution so far. Good. And some other tip is make it readable. So readable means if you name your variable, make some meaningful names, right? Give some meaningful names. So for example, number of participants or n subject instead of capital N, even though you also mean what capital N means, but maybe you want to call it n sub or n sub j, however you call it. And then choose a consistent style. It's like when you are coding up a model, it's really always a good idea that you are thinking that you are coding the model not for yourself, but for other people. So thinking the other people. So it's like, how it's called? I think it's called user-oriented, right? You are thinking that how the users, other people, will use your code. So that as long as you have a tiny little thought about or tiny little concern about what if the other people, they don't understand it? Well, then that's the place to make some comments. As long as you have any concern, then just comment it to get rid of this concern. This is always a good practice. And some other suggestion is start with simulated data. And then this is quite a good practice in the sense that you can start estimating the model even before the actual data collection. So how does that mean? So that means you could use your model as a generative tool to generate some fake data as if they are real data. And then the fake data can be treated the same way as the real data. So you can feed the model to the data, you can feed the model to the real data, but you can of course feed the model to the fake data. The model, they don't know, they are stupid. It doesn't matter to them that the data is real or fake. So this is the role of the job of the researcher. You have to know it. You have to know which is real, which is fake. But for the model, they don't know this. They don't care about this. And why this is important is because if you are fitting your model to generated synthetic fake data, if there is something wrong, that you can already debug your model. You don't have to wait until you get real data to debug your model. You could already fix some possible errors of your model using fake data. And this is really a good practice. I always recommend doing that. And some other tip is like design top-down, code bottom-up, what that means. So when you are designing a model, you might really have the most complex model that you have in mind, right? Because your experiment can be quite complex and you then need a complex model to approximate what the possible cognitive processes are. But when you are coding the model, you do not start with the most complex version. You start with a simpler version. So in our case, to make it a much more concise, concrete, we have in the programming project, we have two models. One is the simple risk Wagner, the other one is the one with differential learning rates, one for the reward, one for the punishment. So if I were to do this coding of the model, I will really start first the simple risk Wagner with only one free parameter, one learning rate. When this works, I make it more complex, adding another free parameter so that it has separate effect for reward and punishment. I do not start with this one because if this one doesn't work, I don't know what to fix. It's too complex. Even though I add one more parameter, but it might require me to think a little more deeper, much deeper, to find out where it's going wrong, right? So always start with the simpler one and gradually add a piece of complexity and then add another parameter and then add another parameter. And then in this case, you're always sure that your simpler version is always working. And whenever you get a new error message, the error message must be related to the newly added component. It must not be related to the simpler version, right? So this is like how you design it. So this is what I mean, design top down, but code bottom up. And the last one is write comment, but this is the same as before. So you write down comments, again, keeping a user-oriented spirit so that when you write down something, think about how the others will read it or use it. Good. And the code never lies. Yeah. This small comment here, this means, so sometimes you have a model, sometimes you change the model, but you forget to change the comments. And this happens to me quite a lot because I was too lazy. I just want to quickly change the code and it works. And I just too lazy to change the comments. And then a few days later, I find out, there's a mismatch between the comment and the code. So what do you trust? You always trust the code, right? And then you change or you update the comment. This is how that works. Good. Any questions here? Pretty easy and straightforward to understand, right, I guess? Good. Let's see. And another topic is the editor. So editor is the software, so where you write down your code. There are a few options nowadays. I just list all of you here for now. So here, what we have been using is RStudio. And then previously, so quite a few years ago, I used this Notepad++. And then later on, I found out there's something called Sublime. So I still use this one a lot. And then there's another one, it's called, how's it called? It's Atom. I think it's called Atom. This is from GitHub. And it doesn't matter which one you use to code your model, right? They are just editors, and then you write it down and everything can be highlighted. So here you see the block name. So here the data block, the word data is preserved for the purpose that this is a keyword to indicate this is the block. This is not a variable name. So then here there's the yellow orange-ish color. And your variable, this W, and they are not meaningful to the program. They are not function names, they're just variable names. So then the color is white, it doesn't matter, no really interesting meaning. So here you see the lower and the upper, and then the function names, like uniform distribution, binomial distribution. So here they are highlighted so that you know which are functions and which are variables, okay? And then this tool has pretty similar kind of theme or layout, but depends on how you customize it, because all of the background color and this color, you can change it pretty easily. And then this one, I don't use it anymore. And RStudio, I still use it. So personally, I use this one a lot for coding STEM models, because I like the user experience of Sublime. Okay. But for you, I guess, if you don't have it or hear this Atom, you can just use RStudio, because there is really one thing that cannot be beaten regarding RStudio, which is the check button, right? So there is the STEM model that you recall in RStudio. We will see that later on. RStudio is able to recognize not only .r files, it could also be able to recognize .stem files. So in other words, STEM file extension, the STEM files, they are well integrated in the environment of RStudio, which also means that RStudio has some specific functionalities regarding STEM codes, STEM programs. So when RStudio recognizes it is a STEM file, then there is a button, right? Like the top right corner called check. The check is like the grammatical check when you are writing a thesis. It checks if the STEM model is grammatically correct or syntactically correct, using that term. And this functionality, it cannot be beaten here. This is not available using the other editors, okay? So guys, for you, it's just use RStudio. And in terms of the color, you can also change it, because if you see what I do, when I was sharing my screen, I also use this kind of color in my RStudio. So same. Yeah. Good. So now let's talk about the errors and the warnings. So I have to divide this into these two parts, because error is something that you have to fix. If you don't fix an error, the program can't go forward, it can't run it. Warning is a little bit different. Warning means something is not so ideal or perfect, but it still runs regardless. So error and warning. We must fix error, but the warning, sometimes some warning we can fix, maybe we have to fix, but some other warnings is okay, we can just ignore them, okay? I will tell you what I mean. So let's talk about errors. The very first one is that you recall that when we are writing the STEM program, each line we run it, we write it, we have, sorry, we have to write a semicolon to terminate this line. Otherwise, you will receive an error. So yeah, you will receive error. And that error message is actually pretty informative. The error message will tell you that a semicolon is expected at line 13, for instance. So then you go to line 13 to find, okay, if there is a missing semicolon. If yes, then add it, and then it go forward, okay? This is easy. And another one is like misindexing, like mismatch or constants. What does that mean? Give you an example. Say we have a variable called x, and we say this is a vector, and there are 5 elements of x. So what you can imagine is that this is a vertical vector. There are 5 elements, and then this guy is called x. Okay, good. This is how we define it in the data block, for instance. And then in the model block, and we have a curly bracket. And then for some reason, we say, well, there is x6. Does that work? It won't work, right? It won't work because there are only 5 elements, and you are trying to access the 6th, which doesn't exist. So then you will receive an error. So this is like mismatch. So what is a constant? Constant means, say you have a x, same here, x vector with 5 elements. So you are about to write a for loop for I from 1 to 5, okay, right? And then each time you ask xi to do something. So this I, this indicator, this iterator, iterates from 1 to 5. So 1, and then 2, then 3, 4, 5, good. And then each step of the loop, it will use the corresponding iterator. So in the first step, x1 is this, and the x2, x3, 4, 5, good, perfect. So constant means here, for some reason, whatever reason, you say, well, this is a 5 here, for some reason. And then this is a constant. So even though you are writing in the form of a for loop, it does looping from the first to the second, from the first to the 5th. But every time when you are trying to run this, it will use the 5th element. It will always use this one. This is really a stupid mistake, honestly, but this happens. This really happens. So when that happens, I will tell you why. So here, if you use a 5 here, if you write a 5 here, you will immediately recognize it because you are expecting to have I here, but then you write a 5, you will really recognize it. I tell you the place where it can go wrong. Say in the data block, I have another variable. I have an integer. I say n, okay? So n is the data, and semicolon. And n equals 5 from our definition. So in R, we prepare for a data list, and we know that n equals 5, good. So what we do here, if I say I, in a for loop, I is looping from the first to the nth, right? Makes sense, good. But if I say here, for some reason, I write this way, this is the same problem as the above one, but this is much harder to recognize because if it is correct to write an I here, but you write a n, and this is a little bit trickier to recognize and to realize. Yeah, makes sense? Good. All right, let's go on. Support mismatch is like, I'll give you an example. Say this happens a lot in the data block. So say in the data block, I shouldn't have erased it. So you have n, okay, good. We have n with 5 elements again. So in this case, maybe x, sorry, x. There are 5 elements of X, good, and each of them, they are integer. And then for some reason in your R data list, the X is not integer. So the X might be something like 1.1, like 2 point something, okay? So this is a continuous variable. And this is called a mismatch. So this here, what you do is that the data is the data, you can't change the data, right? So you have to change the model. So what is correct in this case is that you have to declare X as a continuous variable rather than an integer. So this is called a support mismatch. So the data is not supporting the variable in this sense. And then this is really a good practice to always ask yourself what the data type is. Do you have continuous data or do you have discrete data? And then they have to match up, otherwise it won't work, right? Good. Let's move on. So in proper constraint, this doesn't happen so often. And let me give you one more example again. The proper constraint means this. Say, so you have a variable theta, and you say it's like in the range of 0 and 2. And then later you say, well, this follows the normal distribution 0, 3, right? And we know that normal distribution doesn't have a limit. It's from negative infinity to positive infinity, but then you are fixing that theta is in this range. And so this is kind of an improper constraint. But I think in the current version of Stan, this doesn't really give you a error. It just gives you some improper posterior. But pay attention to this kind of thing, right? So the range and the distribution that you are using is better that, well, it's not better to match up. They have to match up so that they can work properly, okay? Good. The next improper dimension declaration is sometimes kind of, you didn't really recognize what the dimension of the data is in the data list in R. So how you declare the data in the stem part is not corresponding to the data that you provide in R. So this will cause some problem. So just pay attention to what you have and then how you create it in the stem program. And then another one is like vectorizing is not supported. So recall that Stan is a programming language that supports vectorizing in most of the cases. But some cases, vectorizing is not supported. I can give you one example. Maybe this is not so relevant, but I can try. So again, we have something like X. X is again a vector of 5 elements. Good. So if I say X is distributed as a normal distribution, in fact, a unit normal distribution, what we expect here. So we expect that all of the sub-elements here, X1 to X5, is all of the 5 elements in X, they are distributed as this normal distribution, okay? We don't have to write a for loop to instantiate this idea. Instead, we write just X because this vector can follow this normal distribution, vectorizing, right? And in another scenario, let's say, well, I have another X1. Instead of a vector, I have a matrix, okay? Dimension doesn't matter, maybe 5 rows, 4 columns, doesn't matter here, just matrix. And then if I want to say, well, X1, I also want to do this idea, right? So that means each element in this X1, they are following normal 0, 1, but this doesn't work because normal distribution, it supports vector, but it doesn't support matrix. So here is the error, like vectorizing is not supported. You will indeed see this error message. Stan will tell you this normal distribution doesn't support a matrix. Okay, this is indeed an error. So now you might want to ask me, I still want to do it. How should I do it? I still want, wait, let me change the color. I still want each of the elements of the matrix is following this. If I can't write this way, how can I write it, right? There must be a way to implement it. Yes, it is. So in this case, you then have to write a for loop. So the solution is to say, well, for I equals 1 to 5, right? 5. There are 5 rows, and each row is a vector, is a row vector. And we know that row vector also column vector. The vector is possible to be vectorized. So we can just do it. We reduce the dimension from a matrix to a vector so that each vector can be vectorized, of course, right? So here we say a loop and the xi with the dimension here. So then each time this I is changing from 1 to 5, then first place, the first row is following the normal, then moves on to the second row, and then third and fourth until the last, okay? So this is a kind of a workaround to implement the matrix vectorizing. Good. So there's a question to say, can you also apply a multivariate normal function instead? It's not suitable here. In this case, those matrix, they are still following one normal distribution. And if indeed you are talking about 2 dimensions, yes, then it's possible. Yeah. So what I'm saying is that when there is a matrix, 5 by 4, there are 20 elements. So each of the 20 elements, they are independently following a unit normal. So then you will do what I showed you, like write a loop, and then each row can be vectorized by the unit normal. But if you are saying that the matrix is following a bidimensional, 2-dimensional normal, then you will use another distribution. So that's the question you're asking, I guess. Because the 2 dimensions, they're not dependent, and then there is some correlation structure. Yeah, I guess that's the question. And the next one is the round data type. I think I gave this example. If you have a continuous data and then you declare that as a integer, so then this doesn't match. So that there you will have a round data type. And the round distribution names is just like a typo, I think. Just you forget the name and then you misspelled it. Maybe I can give you one example. Regarding this, say in R, if you want to have a binomial distribution, it's like B norm, right? It's like B norm. This is correct in R, but instead you have to full spell it. Binomial, you have to full spell. So this is something that you just have to pay attention to. It's actually still straightforward. Good. And forget prior. Let me talk about that later. And then the last is really a typo, and you misspell something, and then it can't be found by the program. Okay. And then let's talk about the prior thing. Say we have a parameters block. Okay, parameters block. We have this. Good. And then we have a model block. Yeah. And here we say theta is something like 0, 1. Good. Perfect. The rule of thumb is that anything that you write in the parameters block, so here, anything you write in the parameters block, you do have to have a prior in the model block, except that you really want to have a uniform distribution. So let me repeat. Anything you declare in the parameters block, so those are the parameters you declare, you give a range, or maybe you don't give a range, doesn't matter. Anything, any variable, any parameters that you declare in the parameters block, you have to specify the prior distribution in the model block, except the uniform distribution. Okay, I give examples. So uniform distribution is like this. We have 0, 1, and then we say that the parameter is equally distributed between 0 and 1. So anything is like equally likely between 0 and 1. This is uniform distribution. And we know that theta is between 0 and 1, and there is a uniform distribution. In this particular case, in this really special case, you don't need to have a prior distribution, because by default, if you write this way, it is like inferred to be distributed as a uniform distribution. But what if you want something else, right? You want to have 0, 1, of course, that's a range. You want to have something like this, right? In this case, the default uniform prior doesn't work anymore, and then you have to give a proper prior distribution. So in this case, you can say, well, theta is following some distribution. In this case, beta distribution. We didn't talk about that, but anyway, beta distribution is a distribution that defines any shape, really any shape in the unit range. Unit range means 0, 1. So if you want to have like 0, 1, I give you a few examples. 0, 1, those are always 0, 1, okay? If you say, I want to this kind of distribution, I want to a little bit skewed, or the other way around, or maybe even this kind of distribution, okay? Like even this. So anything, as long as your parameter range is between 0 and 1, you use beta distribution to specify it, okay? And it depends on which number you give. There, beta distribution takes 2 parameters, and A, B, and then you change A and B, and then you will see how they look like, okay? And if you really want to know more about beta distribution, the best place to go, Wikipedia, but maybe there's too much text you don't want to read. And recall that I gave you a few weeks ago, there is a link called distribution zoo. So it's a zoo, not animals, but distributions. So there you can change the numbers of A and B, and then to see how they affect the shape between 0 and 1. And this is a really good place to see, to get a intuition, like a feeling how that works. Okay, good. But importantly, let me repeat, anything you define in the parameters block, it has to have a prior distribution. Only except this one. This is the only exception, uniform distribution. Okay, good. But ironically, so why am I talking about this? Ironically, this sometimes it doesn't really cause an error, because if you declare something, but let's say theta, now I don't give a range. Theta by default can be anything if I don't give a range in the parameters block. And then also in the model block, I didn't really specify any prior. That really doesn't give you any trouble, because there is a standard internal procedure to try to find out what can be okay as a prior. But this is really worse than the prior that you give, right? Because you know best what your model is, and you will have to give the prior. And most of the time, the standard solution is not really ideal. So always specify the prior whenever you declare the variable, and then to find if you forget or not the prior distribution in the model block. Okay. So what I'm saying also is it doesn't really cause error, I think, sometimes. I guess I should move it to the warning, because this can give you some warning. So the parameter estimation is not great, okay? So just pay attention to that. It doesn't matter if it's an error or warning, we always need to give the prior. This is the message. Great. Any questions here before we talk about warnings? Yeah.
Yes, I have a question.
Go ahead. Yeah.
We went through the debugging and then tried to do a model fitting. And we received the error message, variable not existent. And we checked the variable was there, but then I Googled it and tried to find a solution. And we thought that maybe adding a data list would help Stan pass, or R pass the variable to Stan, which I don't know. I can if you don't know what I'm talking about, I can copy an example into the chat. But I saw that you never did that, like defining a list, and it still worked in the code that you shared on GitHub and everything. So yeah, I don't know.
I think I need to see your code.
Pardon?
I think I need to see your code. I don't really understand the question exactly.
But
I see what you mean, but I need to see the specific. Yeah, sure.
Okay.
Yeah. Okay.
Thank you.
Yeah, of course. Anything else? Okay, good. Warnings. So there is actually a good list about the warnings. So here, this thing you can click. So there is a brief guide to Stan warnings. What I can summarize here is the very first one is Stan. Most of the time, it's always trying to remind you there is a last blank line, and this is pretty trivial because last blank line is that you code where you stops the last line, you have something, and then you type enter, and then it starts a new line where it's empty. There's, I don't know why, but it's kind of good practice. But the interesting part is that even though you have this blank line, when you are trying to run it, our studio or Stan, they are still trying to remind you, hey, maybe you forget a blank line, so whatever. So this is not important. Okay, you don't have to worry about that. And then this one might be interesting. So maybe you use some earlier version of Stan. What that means. So let's say you are coding your Stan program, the file, using the version of 2.4, for example. And then for some reason, you updated your package. Now it becomes 2.8. There is a huge version jump from 2.4 to 2.8. So usually this updating is pretty incremental. Sometimes can be 2.4 to 0.4.1 to 0.4.2 until it reaches 2.5. So the difference between 2.4 and 2.8 can be really large, whatever. Okay, but for whatever reason, you coded your model in 2.4, and later you updated your Stan package to become 2.8. And then now you are trying to run your old model with the newer version of Stan. And sometimes because of the updating, some function names or something is changed from 2.4 to 2.8. Stan is smart enough to recognize those old variable names or function names. So then it tries to tell you, hey, this is not supported anymore. Please use this and that to replace it. Okay, so they also give the suggestions. So how you can replace your old ones with the new ones. This is a warning, and your old one still works. It's good news, still works. Maybe until 3.1, they will always support the old version. But maybe after 3.1, 3.2, your 2.5, 2.4 version will not work anymore. So there is always a buffer period. So anyway, this is a warning, and until it doesn't work, everything's fine. If that doesn't work, find what is the updated version, and then it will work again. Okay, this is the procedure. And some other warning can be that, say, numerical problems. What can be numerical problem? There are two numerical problems, common ones. So one is like, yeah, I can say 0. Yeah, 1 over 0. This is a numeric problem because this denominator cannot be 0, right? We know from math, simple math. Another one is log 0. This also doesn't work, right? Because if you know the shape of the log functions, this is 0. This never reaches 0, right? Here, this log 0 doesn't work. Those are the two common numerical problems. Of course, you won't write 1 over 0. In the stand code, you never write like 1/0 or log 0. You never write that way because this is so easy. You will recognize it and you can get rid of it. What can be wrong is that if you say you have a if you have a parameter, you have parameter x, theta, you have a parameter theta, and then now this theta parameter, it belongs to, so this sign means belongs to, if I didn't explain, the theta parameter belongs to -1 to 1, okay? Obviously, 0 is contained in this range. So if you say 1 over theta and log of theta, what you can imagine or expect is that occasionally, because here everything is random, there's a Markov chain multicolor, there's a simulation, and then there's an approximation, and a lot of randomness going on. It might be that over the 4,000 or however thousands of samples or visits, the MCMC robots, it might be that once or twice this happens, 1 over 0 happens, or log 0 happens. The good news is that if this is indeed the reason that 1 over 0 or log 0 is caused by randomness, so over 2,000 samples, only once there is a 1 over 0 or a log 0, it's fine. You just can ignore it because there is randomness. We appreciate the randomness. We can get rid of it. It doesn't matter. Good. But if out of the 2,000 samples, like 1,800, we receive this kind of thing, and then you might wonder something is wrong in your code. Okay, good. So usually, if you run the STEM model, when you run it, at the very beginning, it will say numerical problem occurred, numerical problem occurred. If that gets stopped, maybe after 1 or 2 minutes, because initialization, they might encounter this thing. But after 2 or 3 minutes, if that's gone, that's gone. You really don't have to worry about that. But if it just keeps popping up, numerical problem, numerical problem, numerical problem, so often, like from the beginning to the end, then something's wrong. Okay, this is good indication. Good. Something else is like divergent transitions. Yeah, this one we see quite a few times. So divergent transitions, what that means. So we have the MCMC chains. We have 4 MCMC chains. The very best, the ideal outcome of the MCMC chains is that the 4 chains, they mix up pretty well. And then this is called convergence. Divergent basically means some chain, some sample, they go wrong, right? And then you will see the warning message. If you have 3,000 samples, 4,000 samples, let's say 4,000, and if the warning message says, out of the 4,000 samples, 800 samples, they are divergent, then you really have to worry about your sampler. It might be that you didn't optimize your STEM model properly. So optimization we talked about before the holidays. So it might be that you didn't optimize properly, or maybe you just forget about optimization. So the solution is go to that lecture and then to see how to properly optimize your STEM model. Good. And we talk about multiple ways to optimize your STEM model. The most important part is that there is a reparameterization. Reparameterization, if you forget what I mean, that basically means paraphrase, to change the way that you specify your model, but the model is untouched. The model itself is always the same, but you just change your way to describe your model, okay? Paraphrase, reparameterization. And you might just ask me, okay, I did everything correctly. I followed all the steps to optimize the model and the vectorization, a lot of things, everything is okay. But I still receive divergent transitions. How can you help me? This is a little bit tricky because sometimes if you do everything perfectly, and then if you still receive divergent transitions, there are two possible scenarios. One is that your model doesn't work. Your model is just a wrong model to explain your data. Is not correct. You might just try to use another model. And another scenario is this model is still okay, but the model is too complex and the STEM cannot really find an ideal solution. It cannot find the posterior. So what to do? What to do is that we talk about something called STEM parameters. If you recall, we introduced some STEM parameters when talking about optimization. So what are the STEM parameters? The first one is the number of iterations. Say if your model is too complex to sample from by using the default STEM parameter, 1,000 sample per chain after the warm up, then the easier solution is to increase it, right? If that's too complex, I will then need more steps to sample from it. Instead of 1,000, maybe I use 4,000. And then there are some other step parameters, and you can also change that. For instance, to change the acceptance rate, the tree depth, a few things you can go back to see. But the most straightforward one is to increase the sample size. Sample size in terms of how many steps, how many iterations you want your sampler to run, from 1,000 to 4,000. To 4,000. You can also call that chain length, to increase the length of the chain, right? Good. The two scenarios. Let me summarize again, just repeat myself. One is the model just isn't good. You might want to turn to another model. But before you turn to another model, you just have to consider if your model maybe is too complex, and you increase the chain length, so that if the longer chain will still give you a lot of divergent transitions, you might think about maybe the model doesn't work, so go to another model, okay? There is the decision for you as a researcher to decide if which situation you are in. And then this, I cannot really give you any suggestion, maybe just a gut feeling from experience. If I do this, then it's working. If I do something else not working, it depends a lot on experience. You have to run a few on your own, and then so that you build up your expertise and experience. And another warning is like, Stan will say, now I'm Stan, I run the task you give me to run, and me as a algorithm, I hit something called a tree depth, maximum tree depth, and this can be a warning. And the tree depth is one of the STEM parameters that we introduced. So tree depth, what it does, it's pretty complex, but what I can tell you here is that tree depth by default is 10. If that hits 10, that basically means 10 is too small, right? What you do is to increase the maximum tree depth so that it doesn't hit 10. So maybe you can change 10 to 20. Like this is a solution. But so here and here, this kind of warnings. So usually what you do is not to change the chain length or to change the tree depth. What you will have to do is always to go back to your model to find out if there's anything that you didn't optimize properly. Only when you are very sure, when you are very certain that you have optimized everything, then follow the other procedures. like change the chain length and increase the tree depth. Okay, optimization is more important than the power of stem parameters. In other words, optimization is way more powerful than stem parameters. Good. And there's another one, is like, I forgot this one, what that means. Bayesian fraction something information, and this is also written here. Same thing. So if you see this, don't worry. So go back to your model to see if there's anything that is not yet optimized properly. Optimize it first, and then to see if that still happens. An improper prior, and then this is like you have 0, 1 range, but you give a normal prior, so it goes unlimited, and then this can be an improper prior. Oops. Yeah, I think that's it so far. I summarized for you the errors and the warnings. Questions, any? There's a question in the chat, says, tell me something about the error called unserialized stock list, error reading a connection. Yeah, I think this one is like, if you run it from your local computer, it might be because your RAM is full. Might be because of that. So what you can do is that, so we are running by default 4 chains, 2,000 samples per chain. Half of the samples are for the warm up. So what you can do is you run one chain, right? You run one chain with 10 samples to see if you can run through. And if you can run through without a shorter chain and only one chain, if that you can run through, then your model is okay. It only means if you increase the number of chains and the number of iterations, the samples, you receive error. It's because of the limitation of your computer, not the bug or mistake in your STEM model. And it's also possible, another scenario, I think I can't recall that precisely. Another scenario is that because we are running the 4 chain in parallel, right? The 4 chain in parallel. So all of the 4 chains, they run at the same time. This can really cause some trouble if your computer is too old. So it doesn't really support parallelization. So what you can do is, instead of running the 4 chains all together, maybe run the first 2 chains together and then the third and the fourth together. So 2 chains at the same time together. But if this still doesn't work, you can just run in serial, right? So all of the 4 chains, they run one running after the other. After the first chain, then the second chain starts, and then after the second chain is finished, then the third chain starts. So it's like in serial. This might also be the solution. Okay, let's try both. So I repeat, first, use one chain and only a few number of samples, iterations, 10 iterations, one chain, to see that if that works. And then if that works, try to reduce the parallelization. Instead of 4, maybe try 2. If 2 also doesn't work, try 1. And if this still doesn't work, write to me an email. Let's find out together where it goes wrong. All right, does that help? Okay, good. Other questions, comments? All right. So let's talk about the debugging procedures instead. And then we have a break, and then we can work in small groups, breakout rooms, to try to debug the exercise, okay? So debugging STEM, what's the procedure? First thing is that always use a .stem file. So if you have a STEM model, always write that in a separate stem file. That's always a good practice. I see some other people, they write their stem model in a separate, well, not in a separate file, but just as a part of their R code in the codes. So that the stem model is a longer string, and this is not good because you can't take the advantage of using the integrated functionality provided by RStudio. I guess here in the class, everyone is using separate stem files for their models. So this is okay. I don't have to emphasize too much. And when you have the stem model there, and when you receive any, well, before you actually run the stem model, the first thing is to check if your model is syntactically correct using the check button that is available within RStudio, right? Wait. Yeah, okay. The check button is very powerful. And to see in the first place, if everything is grammatically correct, if when you're writing a thesis, it's the same thing. So the RStudio is internally checking if everything is grammatically acceptable. And the second quite informative tip, useful tip is to use the function called lookup. So what does that mean? The lookup is a function that is provided by the rstem package to help you find out how a specific distribution is called in the stem language. Okay, so what does that mean? In other words, if you know that the density distribution function of a normal distribution, d norm, if you know how that is called in R, but you don't know how that is called in stem, so the solution is to use a lookup function to look up in the stem terminology how d norm is called, right? And then the solution is, okay, it's called norm, just called normal. D norm is called normal, and this is obvious. And if we say here, we say d, let's say d norm, right, for binomial. And then here, what you will see is a binomial full spell or something like that. So this function is useful only when you know already what a distribution is called in R. So you want to know how that's called in stem, use lookup. But if you know neither how that is called in R nor stem, then you just go to the stem version. Then you look at the menu. There's a menu PDF. You can download it from their website and then to find out how that's called. Okay. Good. And this one, as I said already, start with simulated data before you even collect real data. You can simulate some fake data, and then you feed your model to the simulated data to see if everything's working. And another quite useful tip is be careful with copy paste, because sometimes you want to just basically repeat what you have done and only change one tiny bit. But maybe maybe there are two instances you have to change and you only change the one, and then this can cause you trouble, right? Really be careful with copy paste. Good. And then here, this is the suggestion actually I gave to Katya. So in her case, she ran the full chain and all of the iterations, there's error. So what you can do is run one chain, run an only one sample, one iteration. So instead of one chain, 10 sample, you can really just run one chain, one sample to see if that runs through. If that runs through with one chain, one sample, you can expand it to be 4 chain, 2000 samples. Okay. And another quite interesting and useful tip is debugging by printing. So the stem is the language that you write your stem file. You cannot select one line and then execute it. This is not the case in R, in Python. So you always have to write your stem model and then call stem function in R, and then it tries to run until it receives an error, if you have error. So that basically means stem is kind of a hidden box. You don't really know where is going wrong, if there's anything going wrong. But this is the same as in other languages, in R, in Python, whatever. You can use the printing function to help you to visualize the internal procedures of stem. Okay, here I give you an example. For example, I received some error, and then the error tells me that the V value here, there's something going wrong. But I have no clue where it's going wrong. I checked everything is okay, but where am I wrong? I don't know. And the solution is I can print it to see in each iteration what the V is, okay? So here, this is the syntax of print. So print is print, good. And here, this is like a helping message to tell me, this is like string, it doesn't change. To tell me when S is S, so this is a variable, S may be 1 in the first place, and then T is T, first 12, okay, and V is 0, for instance, okay. This is help printing message. Also record here there's a semicolon. And how can you know where it's wrong? So I give you a kind of example. Maybe not so helpful, but I try. Recall that you have enough knowledge to be able to understand the value variable. It will be for sure within the range of -1 and 1. Okay, this is our knowledge. We constructed the model. We know enough about how the model works, and we also know the range of the variable. Okay, good. So now you can just imagine where it can go wrong. If you print it, if at some place the value says, okay, -2, oh yeah, boy, then this is a mistake. So why or how come the value is a -2? I didn't really expect that. And then you are sure that in this case, value is miscalculated in some way. And then you go here, depends on the model, and then you find out where the calculation is wrong. And you run it again, you change it, you fix it, and then you run it again. And then until the printing says, okay, good, now the value is for sure. Every time it's between 0, -1, not 0, sorry, between -1 and 1. And then everything's perfect, okay? Good. So what I'm trying to say is, if you printing is indeed helpful, but it is helpful only when you have at least some knowledge about the model. You have to know a proper range so that you are able to detect where it can go wrong. If you don't know this one must be within -1 and 1, and then if you see -2, you might have no feeling of it. But if you know it, then when you see -2, you will immediately spot it to say, hey, this is wrong, okay? Good. And you might just wonder, okay, how can I know this? How am I supposed to know value is between -1 and 1? This is like, there's a learning procedure. You have to build up some experience and then to get used to it. And then you will be able to tell afterwards, okay? Good. And then this is the illustration screenshot of RStudio. And then this is a simple binomial model. And then this is the check button. Always remember to press that in the first place. And then to see if there's error, fix it, press again, maybe new error, and fix, and press again, fix, press again, fix, press again, until when you check it, nothing happens. Then that's good. And then you're able to run the STEM model. And then the check button is essentially effectively equivalent to a function that is provided by the RStem package. So it's not the check button is not magic. So it's actually equivalent to a function, but just you know, it's not really so important. You can just check it. All right. So the next part then is the exercise. We can do it after the break. Any questions, comments so far?